Hello students, in this lecture you will learn the concept of electric field and electric potential. In previous lecture you learned about the force between two charges as given by Coulomb's law. Now these two charges are not in contact but they are separated by some distance. Yet they exert the force on each other. Such forces are called as non-contact forces. Now when this idea was first put forward, the other scientists could not understand this concept of non-contact forces. They said that if the two bodies are not in contact, how these bodies can exert the force on each other? So in order to make the idea of the non-contact forces clearer, it was mentioned that between these two charges there is something which we cannot see or we cannot feel it also, but something is there, and because of that the two bodies are exerting the force on each other. Now this something which is there in between the two charges was called as a field, and in the case of the gravitation it was called as a gravitational field, and in case of the this Coulomb's law it was called as a electric field. Now the electric field was explained by saying that suppose we have space. If you place a charge in that space, that the surrounding space around the charge get modified, and modification that takes place around the given charge is called as a field. Then to find out whether that field is there or not, another charge is taken closer to this earlier charge, and this charge which is taken near to that earlier charge is called as a test charge, because this test charge is going to find out whether there is a field or not. If the test charge attracts or repels, that means there is a field surrounding the given source charge, and this force experienced by this test charge divided by test charge is called as the electric field of that source charge. This is how the electric field is defined. Electric field is a force per unit charge, and unit for that is newtons per coulomb. So here for a point charge, vector E suffix q equal to F suffix q divided by q. Now this vector E is the electric field at some point due to the source charge, and that is equal to force experienced by the test charge divided by test charge. So that is the electric field due to the point source charge in fact. Then to write the expression for the charge surface or charge volume, we have used, see here, electric field is force by charge. So here we have seen the force for a surface charge distribution is given by this. For a volume charge distribution it is given by this. Now by using this definition for the electric field due to point charge, that force divided by charge, so if you divide it by charge you will get the electric field at some point because of some surface charge distribution. So you will get this expression. So Q goes here. So 1 upon 4 pi epsilon 0 integral of surface integral it is, that means double integral sigma r dash r minus r dash divided by r minus r dash cube ds dash. Similarly, to find the electric field at some point due to some volume charge distribution, we use the expression of the force due to volume charge distribution and divide that force by the charge, and what you get is 1 upon 4 pi epsilon 0 integral, it is a volume integral, that means triple integral rho r dash r minus r dash divided by vector r minus vector r dash cube dv dash. Now this electric field is a function of that position, and it is called as a vector function or vector field, as we have mentioned in the first section. So this electric field here is a vector function, because electric field is a vector quantity and it depends on some independent variable. Now in the section 1, in the chapter 1 of vector analysis, we had shown that a given vector function is conservative if the curl of that vector function is equal to 0, and then that vector function can be written as negative gradient of the scalar function, and then that gradient function is called as a potential. Now in this case, the given electric field it is a vector function, and we'll show that it is conserved. And to show that it is conserved, we have to show that del cross E equal to 0. That means curl of the electric field is 0. And once we say that curl of electric field equal to 0, then E can be expressed as minus grad of phi. Phi is some scalar function. So in this case, it will be called as a electrostatic potential. So in order to show that the electric field is conservative, we will prove now that the curl of electric field equal to 0. Now let us consider a volume charge distribution. Now when we consider volume charge distribution, it has a volume, and any volume also has some surface area. So volume charge distribution also contains surface charge distribution. So as we have seen in the previous slide, electric field, we can write it as volume charge distribution, electric field of volume charge distribution plus electric field due to the surface charge distribution. And now let us find the curl of this E, del cross E. You take it on left hand side, also take it on the right hand side. We will evaluate this and show that it is equal to 0. And once we show that it is equal to 0, then you will be able to write E as equal to minus grad of phi, and then that phi will be called as electrostatic potential. Now let us evaluate it. Del cross vector r minus vector r dash divided by the modulus vector r minus vector r dash whole cube. Now this term appears in the integrand of the both the terms for del cross E. Now this del will depend upon that vector r dash. Okay, so you can take it inside the integral, and it will be crossed over this term. Now this we can write it as, we can split this numerator by denominator as 1 by denominator into the numerator. So we have written the del cross as it is, then 1 minus 1 by modulus of r minus r dash cube into the numerator vector r minus vector r dash. Then see, this del is like a derivative. Now it is derivative of the product of the two functions. So it is a product. This is a one term, this is a other term. So derivative of the product, that is uv dash, is u dash v plus uv dash. So here this is u and this is v. So del cross this into this is del of this term, del of first term, derivative of the first term, that is u dash, into the second term. So here we don't try to write cross here, because this is a scalar quantity. So we have to find out the gradient. We cannot find the curl of the scalar quantity. So no. But here what happens is, this is a vector quantity. Del of this quantity, del of the scalar function is a vector quantity. So now r minus r dash is a vector quantity. So you have to write a cross in between. So this is u dash v plus u v dash. So u here is this term, 1 upon vector modulus of vector r minus vector r dash cube, this, into v dash, that means derivative of the second term. So derivative here is like a del, and r minus r dash. Since this is a vector quantity and vector r minus vector r dash is a vector quantity, so you have to write cross in between. Then we have proved in the first chapter of the first section that curl of the position vector is 0. Now these are position vectors r and r dash. So curl of the position vector is 0. So this is 0. So 0 into this quantity is a 0. So second term become equal to 0. Then for this cross r minus r dash gets multiplied here, and derivative of this grade of r raised to n r raised to n minus 2 vector r, and this again we have proved it in the first chapter vector analysis of the section 1. So in this case, see, it is a del of this term. We can write it as modulus of vector r minus vector r dash raised to minus 3. So here this term we can take in the numerator, it will be that power become minus 3. So n here is equal to minus 3. So here minus 3 you will get. Then this raised to n minus 2, that means minus 3 minus 2, that is minus 5. And when it goes down in the denominator, it becomes modulus of r minus r dash raised to 5 into vector r. Vector r here is vector r minus vector r dash. Then next is, see here, now this is a scalar quantity, minus 3 is also scalar quantity. So vector r minus vector r dash into vector r minus vector r dash. So that means it is a cross product of the same vectors, and cross product of the same vector, see vector a cross vector a equal to 0, because it is magnitude is a sign of 0, that is 0. So this term will become 0. So 0 plus 0, so it is 0. And when you substitute this del cross vector r minus r dash by modulus of r minus r dash cube in that equation 1 from the previous slide, so in that equation 1, right hand side becomes 0. So left hand side is 0, and left hand side is vector del cross vector e, and that is equal to 0. And when we have shown that the curl of the vector e is 0, that means that vector e is conservative. And if the curl of the vector is 0, then vector can be expressed as a negative gradient of the scalar function. So we can write this vector e and can be written as minus grad of some scalar function phi, and this phi is called as the electric potential. Now we'll recall a definition of electric potential at a point which you might have studied in the lower class. Now suppose there is a source charge. Let us say the source charge is positive. It can be negative also. So let us say that source charge is positive. Then if you go away from that source charge, the force become less and less, or electric field become less and less. And as one goes to infinity, that force becomes 0 and the electric field will become 0. So at infinity, the electric field is 0 due to a given source charge. Now, suppose the source charge is positive, and if you move another test charge, positive charge, from infinity toward the source charge, then if the source charge is positive, then it will get repelled. So your external agency has to do the work to bring it closer to the source charge. Suppose source charge is negative, then the test charge will get attracted toward that negative source charge. So that system means source charge along the test charge will do the work. So work is done here. Now work done by external agency in taking the unit positive charge. That means work done divided by total charge. Suppose you do the test charge is not unit positive charge, then you have to divide that work done by the total charge which you are moving. So work done by external agency in taking unit positive charge from infinity to that point is the electric potential at that point. And you might have also used this formula, electric potential due to point charge is phi 1 upon 4 pi epsilon 0 q by r. And in terms of the position vector, this r is the distance of that source charge from the point we are finding the potential. So in terms of position vectors, we write 1 upon 4 pi epsilon 0 q divided by modulus, this is the distance, vector r1 minus vector r2. Now similarly, for a surface charge distribution, then what you have to do is, first you have to find the potential due to the charge element of that surface charge distribution, and then you have to integrate over that surface. That is, you have to take a double integral or a surface integral. So for surface charge distribution, potential become 1 upon 4 pi epsilon 0 as it is here. Integral, that charge, that element charge is replaced by surface charge density into the area of that charge element divided by that distance modulus of vector r minus vector r dash. Similarly, for the volume charge distribution, the potential at any point away from the volume charge distribution is written as phi suffix rho, and first what is to be done is, you find that the potential at some point from the charge element which is dq, and dq can be written as rho into dv, and then you take the integral over the volume, and that is a volume integral, and this becomes the formula for the potential at any point due to the volume charge distribution. Then electric field is said to be conservative if curl of vector E equal to 0. That is what we mentioned. Now in this case, the work done, so conservative means work done by that field is stored, is not wasted, it is stored as a energy, and stored energy is called as a potential energy. See, the potential is work done divided by charge. So work equal to charge into potential. Now that work done is stored as energy, and that is called as a potential energy. So potential energy equal to Q into phi. So remember that if the force is conservative, electrostatic force is conservative, the work done is not wasted, but it is stored as a potential energy. See, now example, frictional force is not a conservative force, because if you move the body, then the work done, a heat is generated between the surface of the two bodies. Now elastic force is a conservative force, because if you stretch the rubber band, then if you release it, then it will unstretch itself. For unstretching, it will utilize the energy it has stored during the stretching. So that energy is used to unstretch. In same way, suppose the charge system is there, then in this case the electrostatic force is a conservative force, and suppose that attraction or repulsion is there, then the work done is stored as a potential energy, and formula for that is Q into phi. So now I am solving one of the problem which is there in your notes, problem number 8. 3 equal charges of 1 coulomb each. So let us say that it is plus 1 coulomb are placed in the 3 corners of a square of the side 10 centimeter. Using Coulomb's law, find the magnitude and the direction of electric field at the fourth corner of the square. Now solution, first we have to draw the diagram. So there are 3 equal charges, 1 coulomb each, and they are there at the 3 corners. Let us say that this is corner 1, corner 2, corner 3, and this is corner number 4 of the square. The length of the side of the square is 0.1 meter each. 10 centimeter means 0.1 meter. So this side is 0.1 meter, and this side also 0.1 meter. This and this are also 0.1 meter. Now 3 equal charges, 1 coulomb each. So let us say that all are positive. If you can also consider that all of these 3 charges are negative, the solution will not differ much. So now let us say that at corner number 1, 1 coulomb is kept, column number 2, 1 coulomb is kept, and column number 3, 1 coulomb is kept, and we have to find the electric field at the column number 4. Now, before going further, what we will do is, we will find the length of this diagonal. Use the Pythagoras theorem. Square of the hypotenuse equal to sum of the square of the sides. The square of this side equal to 0.1 square plus 0.1 square. That means length of this side equal to square root of 0.1 square plus 0.1 square. That is square root of 0.1 square plus 0.1 square. That is equal to square root of 2.1 square. So when you take a square root of this, then you will get root of 2 into 0.1. So that is the length of this diagonal, root 2 into 0.1 meter. Now here we would find the electric field at this point. So now there are three individual electric fields. One because of this 1 coulomb at the column 1, other due to the 1 coulomb at the column corner 2, and other at the 1 coulomb at the corner 3. So here what will happen is we can mark here. Say this electric field here, let us say positive, so directed away. So this is that vector E1 is electric field at this point due to the 1 coulomb at the corner 1. See, we have to mark here, since we are finding the electric field here, so we have to mark the tail of that vector here. Similarly, E2, because of this 1 coulomb, so tail is here, E2 is directed this way, along that line. See, the force acts along the line, so electric field also acts along the line. Then a third charge is there at third coulomb, the third corner, that 1 coulomb is there at the third corner. So here, from this point it is directed away from that 1 coulomb. So that is vector E3. So we have three vectors here, vector E1, vector E2 and vector E3. Now we have to find the resultant of this. Now we cannot find the resultants of 3 at a time. We can find the resultant of the 2 vector at a time. Now first we will find the value of E1, E2 and E3. Now here E1 and E3, they are equal in magnitude because the value of the charge is same and the distance also is same. So E1, value of that E1 is equal to magnitude of that E3. So E1 and E3 are equal in magnitude, and by the formula of the electric field due to the point charge 1 upon 4 pi epsilon 0 q by r square. So here 1 upon 4 pi epsilon 0 is 9 into 10 raised to 9. The charge is 1 coulomb and r is 0.1. In both the cases 0.1 and 0.1. Charge is also same, 1 coulomb and 1 coulomb. So when you calculate this, you will get 9 into 10 raised to 11 newtons per coulomb, because electric field is force per charge. So we have found the electric field E1 and E3. Then we will find out electric field E2, magnitude of this vector E2. So this E2 is 1 upon 4 pi epsilon 0, charge is 1 coulomb, divided by square of this distance. This distance is root 2 into 0.1, square of that will be 2 into 0.1 square. So 2 into 0.1 square. And when you calculate this, you will get 4.5 into 10 raised to 11 newtons per coulomb. So we have found the value of E1, value of E3 and value of E2. So now we have to find out resultant of these three. Now we cannot find the resultant of 3 vector at a time. We can find the resultant of 2 vector at a time. Now what we will do is we will find the resultant of E1 and E3. So E1 and E3, resultant of that, I will call it as E13. So now since E1, vector E1 and vector E3 are equal in magnitude, so the resultant will lie exactly in between, making 45 degrees to each one of them. So resultant of this E1 and E3, I have written vector E13 and magnitude E13 by given by the resultant value, which is square root of p square plus q square plus 2p1 pq cos of theta. So here p is E1 and q is E3. So square root of E1 square plus E3 square plus 2 E1 E3 cos of 90, because angle between E1 and E3 is 90 degrees. And cos of 90 is 0, and it will be E1 is equal to E3. So square root of 2 times E1 square, that is square root of 2 into E1. And when you calculate that, when you substitute and calculate, you will get, in fact, root 2 times it is 9 into 10 raised to 11. You will get 12.72 into 10 raised to 11 newtons per coulomb. So we have found the resultant of E1 and E3. Now we have to find the resultant vector E13 and E2, resultant of these two vectors. So we have found the resultant of E1 and E3 as vector E13. So now we will find the resultant of vector E13 and E2. And again we use this formula, but both of them make a same direction. So angle is 0. So since both are in the same direction, we can simply add it. We can use the formula is the square root of E2 square plus E13 square plus 2 E2 E13 cos of 0, because they are in same direction. Cos of 0 is 1, and you will get that E1 E2 plus E13 square root of whole square. So you will get E2 plus E13, or other ways E2 and E13 are in same direction, so their resultant will get added up, and this will be resultant vector E. So I have written here E2 plus E13. So when you add this value of E2 and value of E13, you will get 17.25 into 10 raised to 11 newtons per coulomb.